Hi, my name is Ryan Booz, and I'm excited to be talking about PostgreSQL partitioning at Posette this year. Now, as our databases continue to explode with more and more data every day, partitioning is key to really understanding how to manage both performance and maintenance of your database. And I can't wait to talk to you about it. So this is me. This is where you can find me on social, generally Ryan Booz everywhere. I love to connect, talk about Postgres at all different levels, about Postgres community, and really just understanding how folks are using Postgres in their current roles. So I would love to connect with you at some point. Please feel free to reach out. Now, the agenda for today is pretty straightforward. With 25 minutes, it's not easy to fit everything into a short period of time. So we're going to do our best to do this in a way that's not too fast, but gives you the basics of what you need to know. We're going to talk about the what and why of partitioning, the three different types of partitioning that you can do inside of Postgres, creating and maintaining partitions. That's really what we all want to get to and actually do to manage our database. And then just a couple of tips to understand about Postgres partitioning as you begin to explore it. So let's go ahead and get started. So first, the what and the why of PostgreSQL partitioning. Now, why would we partition things? Now, in our regular life, we actually do this all the time. We have things like file systems. We were used to many years ago, something like a card catalog. We could take things, divide them up into like groups to make it easier to find that information. And in some senses, that's one of the reasons that we do partitioning in Postgres. We can keep like information close together, which can help our queries, help the way that the planner goes about finding that information. But that's not all. We can also think about partitioning as an opportunity to increase throughput and actually, the way that we can scale our Postgres database. Sometimes I think about it in the US, we have turnstiles like this for our interstates. And I think about, there's multiple lanes here, and we can decide how data gets to tables depending on what kind of data it is. So, this allows us both an opportunity to split the data up so it goes to multiple places faster. And at times we can say, hey, this specific kind of data, in this case, if I was an EasyPass customer, I can use these lanes. But if I'm not, I get to go, or I have to go over here to this table or this partition to, just keep things in the right form. So we see, representations of partitioning really every day in our lives, whatever it might be, emails and file systems. But the reality is, the real use of partitioning is mostly about maintenance and then the performance that can come alongside that. Large tables in Postgres, and quite honestly in most other databases, don't scale terribly well. Now, the size of what counts as large has certainly grown over time as, hardware and memory and disk storage space has all changed. But adding partitioning to a table really begins to solve that scaling problem, both in the way that we store the data and the way we query data. So as you begin to move forward and you start to ingest things like time series data, which usually increases in volume pretty quickly, knowing how to go about this is really essential to managing your Postgres database. So what are partitions? In Postgres, partitions are really regular tables. Now, they're tables in today's versions of Postgres that we don't actually maintain. We create one parent table, and we then go ahead and allow the process to create the children tables that actually store the data. And they're regular. They have schema. They have table space. The partitions don't have to reside all in the same table space. Actually, they don't have to reside in the same schema as the parent table. They're attached to those parent tables. And then one of the unique things is recognizing, because they are individual tables, they have all the same things self-contained. They have indexes, they have constraints. However, they themselves, because they are regular tables under the covers, they could also be partitioned further, something we call subpartitioning. Now that gets into a much more complex layout of why and how you might do that, something we won't cover here today. But it is, worth noting that we're just talking about tables used and in some ways disguised as something different within Postgres. Now, this comes around as declarative partitioning in PostgreSQL. Well, there are other forms, and actually still are other forms and ways that you can partition data in Postgres. But starting with Postgres 10, although I generally say Postgres 11 because of a few fixes that really lowered the threshold and made sure that partitioning worked well, began in Postgres 11. And so declarative partitioning simply means that we are saying this is the table that's going to be partitioned, and we declare how the data is distributed among the partitions. We don't have to write triggers. We don't have to come up with an algorithm in a program on our own. We allow Postgres to do that. We get to specify the method. Currently, there are three: range, list, and hash. And then the two things you do need to understand are that partitions need to exist in currently in supported versions of Postgres. They actually need to exist before the data arrives. And so if there is not a partition and you happen to be distributing or partitioning on time, maybe you're getting data for the past and you don't have a partition for that data, you will actually get an error. And so we need to be able to manage those partitions so that you always have a place to store the data based on how you're distributing it. There is a default partition that you can create, which is kind of like the catch-all. However, as we'll talk about briefly at the end, this is really just meant as an emergency, and it actually can make the maintenance of partition tables a lot more tricky than you probably want to deal with long term. So what does it look like to create a table that is now a partition table? Well, it really doesn't change that much. I can take this table, it's a regular Postgres table, has some columns, has a couple constraints and a primary key, and I can simply say, hey, in this case, this looks like time series data, so I want to distribute it based on this payment date. And as I said at the very beginning, this allows us to store records of similarity, in this case, by similar dates, close together dates together. Now, why would we do partitioning? Well, one of the reasons is, again, simply scale. If I were to say select star from payment and I don't have an index on payment date for some reason, Postgres has to scan through the entire table row by row to decide which rows meet this criteria. Now, if we have an index, that's helpful, but there is no guarantee of the order. And so we may actually go through that index. We know which pages of data on disk or in memory to go get that data in, but it's often randomly accessed. They are not close together because we haven't directed Postgres to try and maintain them in a similar table space. Now, with partitioning, we get to take that index. Remember, all of the child tables get all of the things that a parent table has, like indexes and their own constraints. And now, if we form this query appropriately, the master, the parent table knows which partition to go to and can ignore all of the other partitions. And that becomes both a speed up in how we are doing our querying, how the planner can decide how efficiently, most efficiently to go get that information. But one of the other benefits is this: when you have a very large table, you will often hear about tuning Postgres around shared buffers. So shared buffers is the configuration parameter that allows us to specify how much RAM on this computer will be used to cache the data pages that store our data that we're querying. Now, often you want the most recent data to be accessible there, particularly in things like time series applications. If you're only looking at the most recent day of data, you want to have enough shared buffer to retain that. The problem is, particularly when there's random access of data and it continues to grow and grow, we get to the point where this index is so big as one major index and the data and the tables that it represents that it starts to occupy most of shared buffers. And then that means as we do more queries, it's hard to do it efficiently. We have to push data out and pull new data into that cached space. However, if I partition data and I'm mostly querying the most recent partition, then I only have to keep that subset of the index in the data in shared buffers, making more of it available to the other tables and queries that we need to use throughout the application. Then there's one or two other benefits, particularly around data retention and archiving. Now, if you aren't using partitioning and you do something like archiving or particularly data retention by deleting older data, you tend to run into problems. First of all, delete can add locks that are challenging. And delete doesn't actually delete the rows immediately, it simply marks them as ready for vacuuming later on. And so, what you end up doing is spending a lot of time potentially affecting other connections to delete that information. And then you have to wait for the vacuum process to come around behind and actually free up that space. It's not an efficient way to deal with lots of data as it grows to do data retention. And then there's index maintenance. There's a lot of ways and reasons why deleting as a form of archiving or retention becomes problematic the larger a table in a database grows. But with partitions, they are just tables. You can simply drop that partition at some point in the future, and then the data is simply gone. It's almost always a fairly instant operation. It doesn't contribute to table bloat and so forth. Or maybe you want to keep the data and archive it to a cheaper location like object storage or a file system somehow. Well, then you can simply detach the partition so it's no longer a part of the table right now. But if later you need to reattach that partition to query it, you can. So using partitions really makes the maintenance of your large tables so much easier. All right, so that's why we would use partitioning. That's why partitioning exists. And now we need to talk about the three ways that you can partition data inside of Postgres. So the first one I mentioned earlier in my sample table. And I would say this is probably the type of partitioning that's used predominantly and for anyone that's actually doing partitioning with their data. Now, typically, this really works well for something like time series data when you're partitioning based on a timestamp or a date. And again, that allows all of the information for a specific day and time to be close together, even if it's randomly accessed within that one table partition. Now, the other potential is something like object identifiers. So maybe we need to store, a range of information for 1,000,000 rows at a time per partition. Now, is that the best way or method for your application to partition data? I don't know. But there are reasons to do that, and people certainly do. Now, the one thing to recognize is that when you set up your range, Postgres only gives you one option. It takes care of it under the covers. The range that you specify is inclusive of the lower value, and it's always exclusive of the upper value. The assumption being that the next partition will include at the beginning that upper value that you ended with on a particular partition. And so that means in something like time series data, maybe you're partitioning based on a log date. Log tables tend to get very large very quickly. And so in this case, if we say January 1st to February 1st, it would include all the data starting with January 1st, 00000, all the way up to the second or the microsecond right before February 1st, 000. And then the next partition picks up right there and repeats similarly. Now, we are defining this range, so we have to make sure we have the appropriate overlap, as it were, so that no data is lost between partitions. And if you're doing something like an ID, maybe it's a category ID, you're saving all of the information around a category of product or a range of products within partitions. It's the same thing. In this case, 1 to 10 means any product IDs of 1 to 9 if they're integers, and 10 to 20 from that point forward. The second, and honestly used fairly often depending on the application, is the list partition way of partitioning data. And it simply allows you to specify a known list of values somewhere within the table that you're partitioning so that you can specify partitions and say, hey, maybe all of the products that are bike in type go to this partition, or a ball, or they're a drone. Maybe it's regions. Maybe you support, some kind of application across multiple regions of the country that you are in. And so you could specify and partition data based on those specific lists of values. And then finally, you can partition based on hash. Now, this means that you aren't really controlling the value. It has to be numeric in some way. And we're simply saying, hey, we're going to specify We get to specify really the modulus, the way that we're dividing into that value. And whatever the remainder is becomes the partition. And so actually a good way to distribute data randomly and hopefully evenly over time. So if there's no clear partitioning key, hash partitions could be a really good example, a good way for you to proceed or at least test your application. And again, generally, if you have a lot of data and what you are using as your hash key has some variability to it, this can be a good way to distribute that data evenly. All right, so now we have talked about why, we've talked about the type, and now let's go ahead and actually look at how you create and maintain these partitions. So we're going to go back to our table example earlier. Now I've called it something different, and I'll talk about why in just a second. Instead of payment, I've called this table payment 2. And again, we want to go ahead and partition based on that payment date. Now, if I had time to do a demo, I would tell you that the reason I created payment 2 is because you cannot partition an existing table in Postgres. So if I realized that my payment table was getting very large, I would have to create a new table, partition it appropriately, and then somehow figure out when a good time to do is to move the older data over into the partitions. And then I could do a drop rename, something we often call expand contract pattern in dealing with your database and your schema. And then the other thing to note here is that whatever you partition by, the column that you're partitioning by, particularly in a range partition, must be part of the primary key. So if, for instance, this table had started with just a primary key on payment ID, which might make sense, and I tried to partition based on payment date, you would get an error. And so the solution is just to make sure that your primary key, if you are going to have one, includes whatever column you are going to partition on. Now, again, you don't have to have a primary key. And sometimes in something like a time series table, it might not really be that beneficial. Because of time and maybe other foreign key IDs, it's very easy to identify the unique nature of each row. Once we've identified and created that partition table, we can now begin to create the partitions that will store the data. And so in this case, I'm simply creating 3 partitions spanning 1 month of time. We create the table, we name it whatever we'd like. This is a typical naming scheme when you are doing something like monthly partitions. And then you simply give it the constraints. You say, hey, for that table that you're partitioning by this payment date, go ahead and make sure that any of the data in this table is from the 1st of January to the 1st of February. And then we continue on. You can attach and create as many partitions as you want ahead of time. And there are tools and ways to actually help you do that. Maybe you need to create partitions for historical data before you copy it over. So you get control and you have the ability to do that. Now, all administration of the table, adding columns, adding indexes, dropping columns, renaming things, even constraints are all done through the parent table. And so you don't actually, rarely should you ever have to go to an individual child table to do any of this. In fact, if you try to modify the schema of a child table, you'll get an error because you'll notice when we specified the table, the child partitions, we didn't give it any schema. Postgres implied it from the parent and created those partitions to match. And so again, everything you do to a table, any kind of modifications should always go through that parent table. So that would mean something like this. If I want to alter, and add a column, I have to do it on the parent table and it will propagate to all the children. If I want to add an index, again, I do it through the parent table. It will then go ahead and propagate that to the children tables. Now, there are some things like an index that I could add to children tables. There might be a reason for that. Maybe you have a particularly large partition that has some kind of unique value or constraint. It's pretty rare, but some of these things can be done at the child level. But generally, you should do everything through that parent table. One other thing to recognize, and this has become a source of confusion at times when you're dealing with large time series applications, is that when you add an index to that parent table, it is not a global index. Right now in Postgres version 16 and even 17 that's coming, we don't have a concept of a global index that allows the planner to better understand where the data is distributed. Now, it can, as we'll see in just a second, avoid going to partitions if you set it up correctly, but it doesn't have an index that really helps it get to the individual rows in a partition more quickly than going to that table and using the indexes at the child table. So just recognize that. This is simply instructing Postgres to create this index individually at each child table. Now, data retention, the maintenance of your data. Again, as I said earlier, you can simply drop a child table and Postgres won't complain. It just says, oh, there's no more partition that's attached for that particular constraint range. Now, if I want to retain the data, I could detach the partition. And then finally, I could later reattach that partition if I need to query it, as I mentioned earlier. So there are a lot of ways you can handle the data in partition to really help you maintain and query the information you need as efficiently as possible. Now, again, I did tell you earlier that there is this idea of a default partition. Again, it's not created by default. You have to actually specify that you want it for a partition table. It is a catch-all. So this is a way to make sure that data is always inserted, even if there's not a partition that actually matches the range or constraint of that data. It does prevent data loss. You won't get an error saying no partition exists. However, the maintenance of having a default partition can be really frustrating at times. Essentially, what this means is that if I then want to later add a partition for data that's currently inside of the default partition, I actually have to create the data. I have to scan I have to actually, get it to the child table and then do some check constraints before I can delete it. It just becomes a maintenance headache, quite honestly. And so it is often a necessary help, but one that you really have to understand as you begin to use partitioning in your database. And that might look like this. Often I'll see scripts that start in some way like this. I created the partition table by initially, and then the first statement that we create might be this default partition, and which I'm realizing at this moment I have the wrong name on. So I do apologize for that. Normally it would be something like payment to underscore default. And that allows me to identify that partition. Notice there's no constraint. We're simply saying if data is inserted into this table that's partitioned and I can't find a table that matches the constraints, go ahead and use this partition. Now, as you can imagine, managing partitions as your database grows can be a bit of an maintenance overhead. You might have to have a script that runs continually to make sure that you have available partitions. If you know you're going to get historical data, then you have to make sure you do something to create these partitions first. Now, I would say don't rely on a manual process. Again, I've seen this happen, even people that use a tool, maybe like Flyway or another migration tool, to continue to manage their schema. They might try and use that as a way to create partitions over time. But that's not really an efficient way of doing this. Instead, the predominant extension that allows us to do this easily is actually pgpartman. And using pgpartman, or maybe your own pgcron job, a script that you've written, it can run periodically to make sure that everything's happening as you intend. It can detach partitions after a period of time. It can archive data. It can move data to a different table space. It can create partitions into the future so that you are sure you'll have them. Now, there are other ways to do partitioning. Again, not all of these use the current declarative partitioning, but even something like timescale.db is a way to partition your table. And in that case, because they use an older inheritance model, it actually can create the tables for you so you never lose data. And again, Citus, the Citus plugin is another alternative that you can examine as well. So there are a lot of opportunities, but if you're going to use the declarative partitioning in Postgres, you got to use pgpartman or something of that nature. And that is available in all the major cloud platforms for you to use. There's no reason you shouldn't be able to use a tool like this to automate your maintenance. And then finally, I just want to talk about 2 or 3 best practices. Now, a lot of these I've learned over time. I did spend a few years at Timescale, and as we would help clients and customers, have really large time series tables, we needed to help them identify how to make their queries more efficient. So the first thing to recognize is that the general value that most people start their shared buffer space at is about 25% of the available memory of the server. Again, this is just kind of the community driven way of or recommendation for starting shared buffers. However, again, remember at the very beginning, I showed you like the indexes and other things that need to fit in that space. And so when you partition, you do want to make sure that the size of your most recent partitions, the partitions you're querying most often, easily fit into shared buffers. That might mean that rather than a monthly table, if you have a lot of data coming in, maybe you make weekly tables. That will have an impact later, but right now that might actually be the thing that you need so that you can always efficiently be querying the things that are happening. So again, those hot partitions, think about how to make sure they can fit in that shared buffer. You may need to get a bigger server or increase shared buffers in some way. Now, too many partitions can begin to have an impact. In the last few releases, generally 1,000 or a little bit more partitions will increase the planning time of the Postgres planner when it's trying to understand which partitions to go to. So just recognize that. And for very large partitions, again, just ensure that the indexes really are available because the planner will use those constraints to exclude partitions that don't match the where clause or the predicate for the partitioning column. And so then it gets to that table, and we need to make sure we have indexes that can help it find the data quickly, particularly when those tables are very large, those partitions. Second, you always want to filter by the partition key. There's really no value in partitioning if you never use the key that you wanted to partition by, because if you don't, it means that the planner has no idea how to more efficiently go to an individual partition to find your data. And so it will still have to scan every single partition to find the data you want. Now, it might be able to get to each table and then use a different index, but if you're not actually using that partition key, you're still potentially querying all of the data all of the time. So make sure that you are specific and you use that partitioning column. Now in dates, this is still a problem in Postgres. And the problem is just a nature of the planner. When you do something like values of dates, particularly in date ranges, try and use a specific date or time. So if you have a process that dynamically creates queries, try not to use the date math like now minus a month. Now that will work, but it actually will, Postgres has to do a little bit more work, and sometimes it won't be able to prune the partitions or use an index appropriately unless it has the static value first. So really consider this, test the queries that you have, and see if they might perform better if you make that modification. And last but not least, use schemas and table spaces. If you partition a table and you keep those partitions in the same schema, you'll actually see them in all of the tooling. So you end up with lots and lots and lots of tables that you rarely have to actually examine, whether it's in a tool like pSQL or even in an IDE like dbeaver. And so we want to hide those partitions. Often this is easy to do simply with a different schema. Again, you're simply creating a partition that is a table, and it doesn't matter if it's in a different schema, and that might really help with just the maintenance and the overall view of the data as you're trying to query it, because you're always going through that parent table. And then you can use something like different table spaces. I can take a partition that is currently in the default table space, and maybe after a year, I transferred that partition to a different table space that's on slower medium, cheaper mediums, like an EBS volume rather than SSD, something of that nature. Maybe it can even be spit out to cold storage, like object storage using an S3 plugin or similar on Azure. So just recognize that you can use schemas and table spaces to your advantage. And so that is the end of just talking about the basics of partitioning. There's a lot for you to think about and begin to understand and practice on your own. But hopefully this has been a good start, and I would love to talk to you more about partitioning if you want to reach out. Thanks so much for joining, and I really appreciate your time.